Okay, we're going to continue on here. Flip that around. Chapter 17. So we're talking about galvanic cells, really. And remember, with our galvanic cell, we have one side where oxidation occurs, and that is the anode. We have an electrode hooked up there, a little voltage. Uh, Electrons leave as it's being oxidized, travel along the wire to the other side of our galvanic cell, which is where the cathode is. And that is where reduction takes place as those electrons come in to our beaker. We also have, as we talked about, the importance of the salt bridge, which sort of binds both of those together. Again, a reminder that the purpose of the salt bridge, which has usually some type of electrolyte solution in it, is to sort of maintain or prevent really a buildup of the wrong type of charge happening in each of the sort of sides of your galvanic cell. As we talked about, if you kind of took out your salt bridge, you would actually get a buildup of positive charge there on your anode side, which would then obviously prevent the electrons, which are negatively charged, from leaving, and they will basically stay at home there, and your cell would not really run. So that salt solution that's in the salt bridge is really important to keep the level of the charges on each side of the galvanic cell sort of in check, and to keep overall sort of a slightly more positive effect there on the cathode side, which is again what kind of pulls those electrons to the other side. We could calculate the cell voltage, the cell potential, by using our equation of E of the cell is E of our cathode minus E of our anode. And as we talked about in length last time, I think, again, if we are going to use this, we would use it in conjunction with SRP values, which are standard reduction potential values that you can find in a table. Again, because they are all standard reduction potential values in that table, they're all written as reduction reactions, which means technically speaking, the anode reaction is incorrect and needs to be reversed. If you're just calculating E of the cell, again, you do not change the sign. If you're going to subtract with this formula, as we talked about last time, if you do want to change the sign, because again, if you had something like this versus something like this here. I'll get it right there. There we go. Again, if you had your E, whatever this may be, we'll call it minus 0.76 volts, perhaps. If we flip it around, again, the sign of E changes to positive in this case. So if you do reverse a reaction, the sign of the SRP value that you find in the table should be reversed. And if you want to do that and you do change the sign of the anode one, which it will always be the anode one that you would need to change, you then should add those two values together instead of subtracting. So as we talked about last time, once again, that minus there will change the sign for you. So you don't have to worry about flipping the sign if you kind of just put it into that equation. We can identify which one is the cathode or the anode by looking at the SRP values, as long as we are not given any information about how the reaction is happening. We're not given an overall equation or told how the reaction is taking place. The more positive the SRP value in a case like that should be your cathode. And then obviously the least positive one would be your anode. Once again, as we talked about at the end there, if you are given some equation or reaction that's happening, and this is what they're saying is happening in this particular problem, you do need to look at the actual equation and sort of figure out what is being oxidized and what is being reduced to determine which one should be your anode or cathode in that case. But again, in the lack of any of that information given to you other than, hey, you built the cell of these two things, then you could go with the more positive as your cathode. But again, if you are given it, you do have to look at it. We afterwards there tied it into our thermodynamics, I think. Our delta G is equal to minus NF E of our cell. And again, this sort of ties our thermodynamics of spontaneity in with our E of our cell. And a reminder that they should sort of relate to each other. And what I mean by that is if we do get, again, a positive value for E, F is Faraday's constant, which is a positive value. N is a positive value, which is number of moles. That will result there in a negative G, which means the reaction should be spontaneous. And that is what really a positive cell voltage basically indicates. If you have a negative cell voltage, a negative there, along with the negative in the formula, we'll turn our delta G into a positive value. And that will tell us that it is going to be a non-spontaneous process, which means you're really not going to be heading to the product side there. And we will have a negative value for E. We also tied our E into our equilibrium constant because we like our equilibrium constant, and that is RTNF natural log of K. So clearly this is the one you would want to use when you're doing anything that involves the equilibrium constant. You're given an equilibrium constant, looking to find the equilibrium constant. These are all our same sort of characters on both of these guys. So R is our gas constant, which again is the energy version of it. N, as we talked about, again, is the number of moles of electrons. And remember that when we do look at a half reaction, although we will have two half reactions, those electrons should always be the same in both. And we're looking for just the one number. So again, if you had two in each of them, N would equal 2, not 4. So you don't want to add them together or anything like that. And again, the idea there is however many electrons somebody loses should be the same amount of electrons that somebody gains. This also works really the same way as K. So if we do have a large value of K, that would usually result in a positive value for E, which means the reaction would be spontaneous, right? So everything's heading towards the products, and that would mean we'd have more products than reactants, which is why we have the large value of K. We have the small value K, pretty much the opposite is true. We pretty much would be hanging out there on the reactant side, which means not much is happening. And that means that the reaction is probably going to be non-spontaneous and have a negative value for E and a positive value there for delta G. And again, that's why we have more reactants and products in that situation, and why we again have that smaller K value. Any questions on any of that stuff there? All right. Then let us, I think this is where we laid up. Will 1 molar nitric acid dissolve gold metal to form some gold 3 ions? That's the half reaction there for nitric acid, 0.96, and some gold at 1.45. So take some time there, see if it will happen, I guess. So first here, we could figure it out a couple different ways, but we could calculate E of the cell there would be a good thing to do. E of our cell will be, again, our E of our cathode minus E of our anode. So in this case, the cathode is... Which one? The second one. Everybody agree? This is the cathode? Let's go to the first one then, because that's a process of elimination answer right there, I think, at that point. All right, so no, I'm going to say no. We went with that because, again, it was more positive, right? So in this case, we shouldn't think like that again. I feel like I ended the lecture with this exact same conversation. So let's restart. I'm not looking at you particularly, but I feel like, you ever had that like deja vu moment? Like, I feel like I said this maybe once or twice. So let's read the question here and see what it says. We will take nitric acid, or will nitric acid dissolve gold metal, which is AU, to form, that's an arrow going to gold 3. That means when I look at my SRP, which one actually should be reversed? Actually, this one needs to be reversed, which means it's not really our reduction reaction. It's actually going to need to be our anode reaction, right? So in this case, this one's actually the cathode because of the question that is being asked here. It does give us information basically on how this reaction is taking place. So we do have to kind of follow that. Otherwise, we're not really answering the question that is asking. We're answering our own question, which sometimes happens, I suppose. So this again is a case where we wouldn't want to go with the more positive just because it's more positive being our cathode. So with that being said here, we could then roll into our equation. And I'm going to take my correct cathode there, 0.96 volts minus my 1.5 volts. I, again, am not changing the signs because I'm subtracting. And if you did change the signs, you would obviously add instead. So if I do that, that's going to give me a negative 0.544 volts, like a 4. There we go. And here we know that since we did get a negative E of our cell, if we throw it into our delta G equation, that's a negative and that's a negative, which means without doing the calculation, I'm going to hit a positive value for delta G, which means this reaction is non-spontaneous. Yes. And we really could have stopped with the negative E there and know that it was going to be a non-spontaneous reaction because of the negative value that we have for either cell. So the answer is no, it will not. What we learned from this is if we're given the reaction or told about it, we're going to look at it and see what is being oxidized, what is being reduced. And we could even see that here if we look at the gold when we got it in the right orientation. Again, it's going from 0 to +3, which means it's becoming more positive and being oxidized in this case. All right, good times. Let's try another, shall we? All right. What is the equilibrium constant here for this reaction? Here's our SRP values. Give it a go. So just come up with. Okay, so let's take a look. So clearly I see equilibrium constant. I have some SRP values. So I'm going to go with the equation that has those things in it. That's a RTNF, by the way, no negative there. Natural log of K in this case. So we do need to calculate perhaps our E of our cell since we are going to be looking for our K. And we are going to know that when we look at this equation, we're going to actually look at it and see that the iron is a +2, right? And goes to 0. So that means the iron is being oxidized or reduced in this case. It is being reduced, right, as it started out like over here, and it is ending in that direction towards more negative. And in this case, the silver is going from 0 to +1, which means it's starting there and heading in a more positive direction, it's being oxidized. So in this case, that would mean that our iron is our cathode, right? And our silver here is our anode in this case. So our cathode would be our iron 2 plus a couple of electrons heading over to our iron. And again, that would give us an E that's minus 0.44 volts. We have our anode, which would actually be our silver, dropping off an electron along the way. And since I did flip it, technically speaking, for the reaction that I wrote, the E value would then change to a minus 0.80 volts for how I wrote it. Also, before we could do anything, if we want the overall reaction, we could see that we would need to multiply this guy by 2, which is how those 2's get into the overall reaction. And that's important because that also tells us that N is going to equal 2 in this case, right? So we want the balanced number of electrons that are being lost and gained. So we could do our E of our cell. So I do have 2 options here. Since I actually changed the sign, I could just add those 2 together. Or you could still go into your original kind of subtraction version where you would not change the sign. So if you did the subtraction version, you would take minus 0.44 volts minus our 0.8 volts, which again is going to change the sign for you. If you change the sign, you would then just add those together, whichever way you choose. You both should end up at the same number, hopefully. And that number is a minus 1.24 volts. Yeah. Any questions so far on that there? By the way, just from that number, would we expect this reaction to be spontaneous or non-spontaneous? Which also would we expect now to have a large value K or small value K? Should we end up with a small value K? So again, all those things should work together, right? So let us get into that part of the calculation. I think we got everything we need. Again, Faraday's is a constant. We're going with 96,500, I think. Yeah, joules per mole. All right, so putting this in, negative 1.24 volts equals my 8.314 joules per Kelvin per mole. Our temperature does need to be converted into Kelvin, so add a 273 to that, gets you 298. Going to be divided by our 2 moles. And our Faraday's constant, 96,500 joules per volt per mole. So we're gonna get a lot of stuff canceling out here, and that's gonna not equal. That's gonna be the natural log of K. There you go. All right, so I'm gonna clean up to the left there of the natural log. We're gonna take 8.314 times 298. We're gonna divide it by 2, divided by 96,500. Gonna give us minus 1.24 volts equals 0.012837161. I felt like writing all the numbers. There you go. We're then going to divide this to the other side. So we're going to take minus 1.24 divided by that number. And that's going to get us a minus 96.5945-ish, 6, equals natural log of K. To get rid of the natural log, we're going to take the E of both sides, like I think we did previously when we were doing some kinetics action, I think. When we do the E of this side with the natural log, it just gets rid of the natural log part. And if we do it to the other side there, if I find my button, we're going to end up with like 1.1 times 10 to the minus 42, which I would say is a small value of K, which again does all sort of make sense. Positive value of G, negative value of E, small value of K. Yeah. I wrote it, what I wrote was the flip version. What you would find in the table, it would look opposite that. It would look like this in the table. So that would be the SRP reaction that you would find in the table. So I flipped it because in this case, the silver was our anode. And that's why when we would take these two reactions here, if we added them back together, our electrons would cancel and we would end up with our iron 2 and our 2 silvers on the left, and our iron and our 2 silvers with a +1 charge on the right. If we add those back together, that's how we get to the overall reaction. So you would find it in the table looking like this, and that's the one you have to flip. Again, because that table has all reduction reactions written, so it's always going to be the anode one that if you needed to write the reaction or something like that, that's the one you would need to flip. Other questions? Fun calculation. So now let's talk about the effect of concentration on cell voltage, and everybody's favorite equations. Good talk. Let's go back and talk a little bit more, maybe. All right, so taking a look at these equations that we saw previously, some of our thermodynamic equations, obviously some of our E of cell and thermodynamics equations. When we put them together, we get a very useful equation, which is the Nernst equation, which is this one right about here. These two versions down here is much like the equation we saw with the equilibrium constant, where at 25 degrees, kind of R, T, and F are all constants. So they reduce down to those bottom two equations, which you'll sometimes see people use. And again, that's our natural log or base 10 log. If you don't want to worry about those two, again, just the one in the box, and you could just put the numbers in at 25 degrees and everything like that. Let's talk about what all this is. We have two E's, kind of like when we had this equation of delta G in that chapter. One of them is sort of under like non-standard conditions, again, is what you could kind of think of it, and the other one is under standard conditions. So this E here, again, you could think of as like non-standard conditions. So what does that mean? It means kind of the same thing we talked about when we talked about it up here. That is, you maybe have a concentration that's not 1 molar. Maybe you have a pressure that's not 1 atmosphere. Maybe a temperature is not 25 degrees. So those three things are sort of what's considered standard sort of conditions when we talk about thermodynamics and these type of calculations. So if you're given pressures or you're doing something where those concentrations are not 1, basically, you are under those non-standard conditions. This E naught, and that's what the naught sort of means. It's sort of like the standard condition situation. Is our one that we've been using, our E of our cells, our E of our cathode minus our E of our anode. The R, T, and F and N, they're all the exact same thing as previously used in that example. Q is our reaction quotient, right? And that again is our products over our reactants. And again, we calculate the same way as we calculate K. And we still obviously take the coefficients as the exponents, just like we would do in a normal situation. So we use this for situations, like I said, that's sort of under non-standard conditions. That equation that we just used with the equilibrium constant is sort of derived from this one. So if you want not to have to remember the other one, you could actually just get that one from this equation too. And that is because when we hit equilibrium, E will equal 0 and Q will equal K, which means if you get rid of that, you get 0 is equal to E naught minus RT NF natural log of K. And if you bring that entire side to the other, you get the equation we just used in the previous example. That's why there's no negative on that one, because we add it back to the other side. So that one that we just used with the equilibrium constant can be derived from the Nernst equation by making that first E 0 and Q make a K and solve for E, and you could get that other equation that we use as well. Question on that there? Yeah. All right. So let's try perhaps, yeah. All right, so in the following reaction, does it occur spontaneously if we have 0.6 molar iron 2, 0.01 molar cadmium in this reaction? And again, here's some of our SRP. All right, so will the following reaction occur spontaneously here at 25 degrees Celsius? And we have some concentrations given to us. So we do want to use the Nernst equation here, and really this is the key to tell us that we should use the Nernst equation, because these guys are not 1 molar. So this is the non-standard conditions here. When you do something like E of the cell is the cathode minus the anode, and you go to that table and you look up the SRP values, it is pretty much in that table. Everybody's 1 atmosphere, 1 molar, 25 degrees, and that's standard conditions. So here, that's what's really going to be sort of the non-standard part of this calculation. And again, that should direct you to the Nernst equation, which would be our E is equal to our E naught minus our RT NF natural log of Q in this case. And that's why we would choose, obviously, to use this equation. Any questions on that? All right, so we got a few things to calculate here before we get into the actual calculation. We do want to also figure out our cathode and anode, and I know you will then be going to the equation since they gave you the equation, and you would looked at the iron and saw that it was +2 versus 0 on the other side, which tells you the iron is becoming more negative, right, and being reduced, and means in this case that it is going to be the iron here that is our cathode. While we look at the cadmium here, it goes from 0 to +2, once again moving to the right on that number line, becoming more positive and is being oxidized, which means that this guy is our anode. They were both negative values for SRP, but in this case, if you went just by the SRP values, you would have chose cadmium as your cathode versus the other guys. So again, you want to make sure that you do look at it. So if we write the reactions which were given to you, I think in the handout there, it won't always be obviously given to you. So what we have going on here is our cathode is just the way we would find it in the table, which would look something like this. And that's going to give me this, and our E would be minus 0.44 volts. Once again, this technically, when we look in the table, we will find this reaction given to us with our E value there again of minus 0.40 volts. Once again, if we wanted to write the equation or use the equation correctly in this application, we would need to flip it around and make it our anode. And again, if we did that, we would then turn our E value there into a positive value. Any questions on that? Again, looking at these half reactions, we could also figure out our N from it, which is 2 in this case, right? So N is equal to 2. We could also, at this point, calculate our E of our cell under standard conditions, our cathode. And again, here, I'm going to do cathode minus anode, so I'm not going to change the sign. If you did change the sign like here, again, you would add the two numbers as we've been talking about. So our cathode here is going to be minus 0.44 volts. Minus 0.4 volts. And again, those two minuses change it to positive, which is what it should be. And that's going to get us here. I did pull out the calculator. There we go. 0.40. Minus 0.04 volts. So under standard conditions, would this reaction occur? No, because we do have a negative value, right, for our E of our cell, which should again give us a positive delta G and so forth. But we're not under non-standard conditions, so we're going to now see if maybe playing with the concentrations here can turn this reaction maybe into a spontaneous reaction by changing around the concentrations. So the other thing that we need is Q, and again, Q is our reactants over our products, which in this case would be the concentration of cadmium divided by the concentration of iron 2, and just like normal, the other two are solids, which means they should not be included. And that's also why you only have two numbers given to you, right? Is for the aqueous ions that are floating around. So put in our numbers for that. That's going to give us 0.01 divided by 0.6 in this case. And that will get us 0.01 divided by 0.6. 0.016667 there. We'll throw the 7 there. So now we got our Q and we have our E over cell. So we really now have everything on the right hand side here of the equals. So we're going to go minus 0.04 volts minus our R, which is 8.314. Our temperature also needs to be converted to Kelvin, so 298 on the Kelvin conversion, divided by our N, which again is 2, and our constant 96,500 joules per volt per mole, and our natural log of our Q, which is 0.016667. All right, so cleaning up everything on the right there, I'm going to start with the natural log of that number. I'm then going to multiply it by 8.314 and multiply it by 298. I'm then going to divide it by 2 and divide it by 96,500. And that's going to give me minus 0.040 minus 0.05255-ish as well. At that point, I'm going to finish the calculation by taking minus 0.04 minus a negative value that I have there. Those two negatives are going to turn that guy into a positive, I hope. And it's going to give me a whopping cell voltage of, we'll call it something like that, 0.013 volts. Is this reaction spell? Yeah. Yeah. Negative 0. Yeah, are you talking about this number right here? Yeah, so that number right there would be what this cell would be if you built this cell under standard conditions, with your iron being your cathode and your cadmium being your anode. So if you built it under standard conditions, all the concentrations were 1 molar, you would end up with a cell voltage of minus 0.04, which would mean under those conditions, it would not be a spontaneous reaction that would occur. Now, with playing with sort of the concentrations that are not 1 molar in this case, we did end up with a positive voltage, which means in this case, it would be spontaneous. Not a lot happening in this case, but by playing with those concentrations, what we were able to do really is kind of turn this non-spontaneous reaction under standard conditions into being somewhat spontaneous by playing with the concentrations. It will be, because when you calculate E and you put it into that delta G equation that we saw earlier, because of this negative, it basically means that if you ever end up with a negative value for E, those two negatives will always turn your delta G into a positive, and a positive delta G means the reaction will be non-spontaneous. And that's why always, you know, you kind of want usually positive voltage when you build it. So when you do the positive voltage plus that negative or times that negative, it will always end up with a negative delta G, and that means that that reaction should always sort of take place. And that's why when we choose to make a galvanic cell, when we choose to make a galvanic cell out of just two things and not really knowing which one's which, that's why when we choose the more positive value for our cathode, that usually means it'll probably be a larger number, right? So when we subtract it from our anode, you're going to end up with a positive value, I'm sorry, for RE in that case. So that's why when we want the cell to work, we choose that guy with the more positive value, because that will usually end you with a positive value for E, which would then mean you would have a spontaneous reaction that occurs. Other questions? Yeah. So this demonstrates that you can play with things like concentrations. If we happen to have a reaction that had some gases in it, you can play with things like pressures as well. And by changing the concentrations or the pressures, you can, like in this example, turn a reaction that under normal conditions would be non-spontaneous into being sort of spontaneous. Again, you're not generating a heck of a lot of voltage in this particular example, but it is positive. Other questions on that? Okay. All right, let's try one more here. For the following reaction, calculate E and K. Look, so we're looking for a few things here. If you rolled with the Nernst equation, which is this that we just saw, we clearly are looking for the equilibrium constant, which means you should not be using that equation, right? So you should turn that equation, because it's at equilibrium, E is equal to 0. Once again, Q would equal K, which means basically we end up with our guy that looks like this. Going to bring all this to the other side, and we get the equation that we used previously, which is this one here. So again, in case all fails, you can still get to the equation that you need by going through the Nernst equation. I guess if you don't remember the Nernst equation, then that's not going to be helpful at all, I suppose. So we are looking for K and we're looking for E. So I'm going to assume that we want to go with E for first here. By the way, to balance this, we could clearly see we have 2 electrons here. We do need a couple of electrons here, which really means that we should probably end up with a couple of 2s up there to balance out this equation when we would put it together correctly. Now, looking at this, we want to figure out which one's our anode and cathode. And again, we are given the equation, so we want to look at it. Now, again, the good thing about redox is all you have to do is figure out one, right? And the other is the opposite. So perhaps chromium is the path of least resistance to figure out what's going on. That's a +2. That's a +3, which means obviously on the number line there, we are heading in that direction, which means this guy is being oxidized, right? And by default, this guy would be reduced. That means that if you blew past that part, you still would have been okay because you went with the more positive one here and you got lucky. So that's going to be our cathode, and that will be our anode in that case. Any questions on that? By the way, out of curiosity, the oxidation state of the sulfur on the left is with a -10. So 10 divided by 4 is like a 2.5 maybe, yeah? What? I know. That is a -2. That's a -6. That's a -2. So that's like there's 2 of them there. So I don't know what that's got to be there. So we want a 4. So that's like a +2 maybe. So it goes from +2.5 to +2, which means it actually is slightly moving in the other direction there to the left. By the way, you could also look at the other definition of oxidation and reduction, which is that sulfur, as it goes from left to right, less oxygen attached to it there. And that also is a definition of reduction. So we're going to calculate our E of our cell now that we got all that worked out. Maybe some parting gifts or something like that would be good. So our cathode is going to be our 0.17. I'm going to subtract it, so I'm not going to change the sign there of my anode. We'll do a little bit of that action there, and that's going to get us a 0.17 minus a minus there 0.5, 0.67 volts. I hope. I'm going to try that one more time just to make sure. Super slow replay here. There we go. Still 6.7. So that's good so far. That means that my E of my cell here is positive, which is going to tell me a bunch of stuff like this reaction is. Let me try the other hand. This reaction is, there it is. It is spontaneous. That also should mean when we calculate our K, small, large, large. There it is. All right. So let's just move on to the next problem. No, I'm just kidding. All right. So we got our E. We have all of our guys here. Now that I did give you the temperature, we also can see again that our N is equal to 2 from our half reactions. So put in our numbers there. 0.67 volts is equal to 8.314, our 298, and our 2 moles, and our 96,500 joules per volt per mole, and natural log of K in this case. Going to clean up there to the left there on 8.314 times 298 divided by 2 and divided by 96,500. And go up high, I think here. 0.67 volts is equal to 0.012837 natural log of K. We're going to divide this to the other side, right? And that's going to be 0.67 divided by that number. Going to give me 52.192. Not sure what I just heard there, but I'm just going to continue. I'm going to push through it. That's what I'm going to do. I'm going to push through it. At this point, I need to do a little E action. Why not? What's E both sides? Again, going to get rid of that. And dare I say at the end here, we're going to hit a 4.6-ish times 10 to the 22. That definitely would be a large value of K. I will say that now, depending on a couple of factors here, when you do your E, and depending on how you round, you may get a slightly different number for the front part, but the times 10 to the 22 should hopefully still be there. Also, if you happen to use one of those kind of converted equations where they got rid of the R, the T, and all that, and went 0.0257 volts and stuff, you may get a slightly different answer depending on rounding, especially when you're kind of doing the inverse of the natural log and stuff like that. So, but the exponent part should still be pretty close. So if you did round a little bit differently, you might get a slightly different number there in the front, but that exponent should still be good. Question on Nernst equation, calculating K, E, B, C. Yeah. All right. So continuing on, let's talk about batteries. Why not? Because that seems what's on the slide. So we're going to talk about batteries here. You're not going to be responsible for all the individual reactions for the different types of batteries or anything like that. But we are going to go through some different types of batteries briefly. And you just need to know basically how a battery is similar to a traditional galvanic cell that you build in a laboratory and how it varies a little bit different than those. And that might just be the exact question, by the way, on the test there. So that's essentially what you have to know. And again, you have to know specific reactions for each type of battery. But batteries, in a sense, are really just a galvanic cell or a series of galvanic cells that are basically hooked together for direct electrical current at a constant voltage. They're self-contained, so you don't have sloshing beakers as you try to hook up your car or whatever to it. Or, you have no need for a salt bridge as well. There's other things that are used in place of a salt bridge that sort of function very similar to it to help sort of keep the charges for sort of building up. But batteries, essentially, as we sort of talked about a little bit the other day, they really do function the same way because they are sort of galvanic cells. And again, that's why when you put your battery into the battery compartment, you want to put it in the right orientation, because it's pretty much similar to a galvanic cell. If you kind of hooked your electrodes up backwards, right, they wouldn't work. So if you unhook up and put it the other way, it will work. And same idea, obviously flip your battery around, it will kind of be in the right sort of direction. So let's take a look at the first type of battery here, which is sometimes referred to as a dry cell. In this case, I'm going to go with perhaps Duracell, as it looks like the copper top there. I don't want to pay the royalties, but maybe it's the Duracell battery there. That's also known as a, well, I'm not going to pronounce it correctly. Anyone? Yeah, I like it. That sounds right. Like I feel if you just move the hands a little bit as you say it, I think it makes it better as well. You know, I think that's how you'd say something with, you know, the little mark there. So I don't know. We went off the rails here, didn't we? Off the tracks. All right. So the anode here in this case is actually the zinc can that's in contact with a strong electrolyte like MnO2. The cathode is actually the carbon rod. That's also why there are positive and negative here, right? So that's our zinc anode where oxidation occurs. Yes. So that's electrons leaving, going through the wire that's usually in the battery compartment, right? To the cathode, right? Which is on the other side connected to the wire there in the battery compartment. And as those electrons go out and about, they power your calculator so you can do all those wonderful chemistry type problems. Yes. You go like, my battery's out, I can't do my chemistry problems in this case. So clearly it's all self-contained. This type of battery has a voltage of 1.5 volts, no matter what sort of size that you have, right? You have AAA, AA, C, D batteries, all those type of things. They just can kind of continue this reaction for a lot longer, right? The bigger the battery, right? So it has more ability to sort of keep it running for a long period of time. If we look at our anode reaction, we see our zinc going from 0 to +2, again, losing electrons, being oxidized. And then again, over here, we have our cathode, which are gaining those electrons. This sort of middle part here, if you will, sort of acts as like a salt bridge in a traditional galvanic cell. Again, electrolytes, right, are things that break apart into ions, right? So strong electrolytes will produce ions. So it's almost the same sort of effect as the salt bridge, where it obviously has an ionic compound and those ions are going to one side versus the other. Sort of helps keeps everything flowing and not get a buildup of charge all over the place. Also the stuff that you see as it starts leaking, right? As you keep batteries too long and it starts coming out of your battery and all that nice white stuff everywhere, right? Still looks good. We'll put it in the compartment over the best, I suppose, at that point. Or if you leave your battery in too long or your compartment, you pull it out, it's all crusted up and all that stuff coming out of the inside. Another type of battery is a mercury battery. It's used a lot in medicine and electronic industry. It's a little bit more expensive. It has also a zinc anode, and it's in contact with a really strongly alkaline electrolyte. Alkaline means basic. Yeah, there it is. Basic. So we have something like we can see here, potassium hydroxide, which is a strong base. Once again, sort of functioning like the salt bridge. And we have our anode, which is our zinc, and our cathode, which is our steel rod here. One of the things that makes it a little bit more expensive and also why it's used for medicine and things of that nature is there's really no change in the electrolyte composition during operation. And the overall reaction, if we look at it, basically contains solid substances. So that's really the key for a lot of batteries is if you kind of make solids on both sides and stuff like that, and there's kind of no change in that electrolyte composition during the reaction, that's going to allow it to really run for a long period of time and continuously sort of run. It also gives some of these things rechargeability and being able to recharge based on having those solids present there in the reactants and the product side. You get a little less of a voltage there happening there at 1.35. But because of that kind of no changes is happening, it does run a little bit longer. And once again, it's our zinc here going from 0 to +2 being oxidized. Our mercury, dare I say, that is mercury 2, I believe. And that is mercury with no oxidation state. So that is being reduced there, as is going from 2 to 0 in this case. Lead storage batteries, that is like your car battery. Yeah. They are basically a series of 6 identical cells together. Each one has a lead anode and a cathode made of lead dioxide. They are immersed in some type of battery acid, which is why the term is called battery acid, some type of acid like sulfuric acid. Again, is a strong acid, so it's going to be a strong electrolyte, again, keeping everything flowing like salt bridge. Under normal conditions, each of those cells can produce about 2 volts, gives you your 12-volt battery in your car. And that's enough to turn it on and get everything started, unless you're in a rush and late, and then it won't turn on and it's dead, right? And you got to call AAA and all that good stuff. And you hope it's not your alternator, right? When that happens, right? And we do have things like alternators and stuff like that, so we don't drain the battery, right? It's sort of rechargeable as it's going through the driving process, so the power doesn't go one way or the other along the way. It's rechargeable. And a good battery can be checked with a voltage meter would be a better way to do it. But you can also look at the electrolyte composition or density of it, and it's like 1.2 is good. Also, in colder weather, sometimes have some trouble because it's cold, so things get more viscous, right, from the weather, and prevents some things from flowing. There's a cross section of your car battery. Don't cut it open. Right? They don't recommend that, I suppose. There's our positive terminal there, our negative terminal. And again, here, if we look at the lead, is going from 0 to +2. So again, being oxidized. And actually, in this case, we have our lead over here going from +4, I think, on that side. That's like a -2, it's a -8. It's -2 +2, I guess would be a better way of saying that. So we'll end up at +2 on that side, again being reduced. And this is lithium batteries. Lithium batteries are light metals, so they're used for a lot of things like power tools. You use lithium batteries, cell phones, those type of things. We have an anode, which is a carbon graphite material that has holes in it. That actually allows the lithium to sort of migrate across to the other side, and it has some type of transition metal as the cathode. These guys can be recharged hundreds of times, which is why they're used for things like that, power tools, cell phones, and those type of things, without deterioration, again, because this has this sort of solid on the beginning and end, which allows it to be recharged a lot of times. A fuel cell, which is not really a traditional battery, but sort of functions like a battery. A fuel cell, like a hydrogen fuel cell, which is what we're looking at here, which is what they originally wanted to make cars run on, right, was hydrogen fuel cells, because the only thing that you made at the end of the reaction was water coming out of the tailpipe, right? So less polluting and stuff like that. But hydrogen is a little bit different than gas, and the pumps are a little bit different and so forth. So it didn't really pick up all that much. There are some. So this is a fuel cell, which requires obviously oxygen and hydrogen to come together. And here's the hydrogen that is going from 0 to +1, and the oxygen going from 0 to -2, again being reduced in this case. And we're sort of the same way. Obviously, you need a constant supply of sort of hydrogen, oxygen we could get from the air driving around, but you would have to fill up your gas tank there with hydrogen. I don't know how we got to the South Coast Air Management District, but we did. But actually, they do a lot of that type of stuff where where they look at where environmental stuff that happens and air quality all around California. And when something happens, they like give out reports and stuff. All right, so let's talk about corrosion. Like this lecture is going right now, is corrosion. So corrosion is returning metals to their natural state or their ores. A lot of steel that's produced is really just produced to replace metals that start to rust. All metals that have an SRP value less positive than oxygen is susceptible to going through corrosion. SRP is standard reduction potential, and that means if I have a metal and I have oxygen and the metal is less positive SRP, that would mean it's more negative, and my oxygen would be more positive. That means which one would be my cathode in this galvanic cell of life? Oxygen would be my cathode. That would be my metal would be my anode, and where oxidation would occur, which is why the metals start to deteriorate, right, and go through corrosion, because basically they're being oxidized, right? And when they are being oxidized, essentially what that means is in most cases they're going to be losing electrons, which means they're going to jump from the solid off, right? And that's why the metal starts to deteriorate as it goes through that. So that's essentially what corrosion sort of is basically these metals going through oxidation in a spontaneous sort of process. So it's just naturally occurring. Not much needs to be added to the mix for that to occur. Most metals, though, will actually form a layer when they go through oxidation. That's not necessarily a bad thing. So not all corrosion necessarily is a terrible thing, because what will happen sometimes is as it goes through corrosion, it will create a layer that will sort of protect the non-corroded metal underneath. So it prevents it from further corrosion. So for example, aluminum will form a nice little layer that will kind of protect the metal that's inside. Iron does that as well, but the problem with iron is it falls off that protective layer, so it's not much of protection at that point. And obviously, as something that is rusted, if you have a piece of rusted metal, you could just click it right now, you could basically break through it, and that obviously exposes fresh metal underneath to continue the process of oxidation and going through corrosion. Copper forms a lovely greenish patina, right? So people pay a lot of money for that corrosion, right? I suppose to get that effect. Silver tarnishes with silver sulfide. Gold, which has a value of 1.5, is a larger SRP value than oxygen, which means that it will not go through a lot of corrosion, because when you hook up oxygen and gold, oxygen is more positive and gold's more positive and oxygen is more negative in terms of the SRP value. That means in this case of this galvanic cell, which one's my cathode? It is going to be the gold, as it's more positive, and all the anode oxidation is going to happen with the oxygen, which will mean my metal of gold is not going to happen much to it, which might be why gold is quite expensive, right? Not much happens to it. So speaking of rust, pretty much for rust, you do need a couple of things to happen. You need a little bit of iron, a little bit of moisture, and some oxygen, and you have all the makings for rust to occur, which is iron 3 oxide. It actually happens in two processes. Actually, iron then gets oxidized to iron 2. And then it continues through oxidation to iron 3, and then it combines with some oxygen to make the iron 3 oxide, which is our rust. As you can see here, there's a lot of little pits on metal, which are great places for moisture to sit. And when moisture sits on that metal, and obviously there's oxygen in the air, you're going to create a lot of rust that's going to happen. Once again, the problem with this is it can fall off, and then you create more rust, and that falls, and more rust. And then you need a repairman, because now you just, rusted through that whole piece of metal right there. Going to probably cost you a lot of money, which I imagine why the money bag is right there and present as well to replace that. Any questions on that there? Now, there's a few ways that we can prevent it. Some ways to prevent corrosion. We could apply paint or a coating to it. That is like Rust-Oleum paint. I'm imagining that's why the name is called Rust-Oleum paint, right? To protect it from rusting, I assume. I could be wrong on that. I might be wrong. Could be just making this up as I'm talking, which I probably am. We also could do the process of galvanizing, which again basically adds a little layer to it that protects the metal underneath it. And so when we add some zinc to, say, iron, when we look at the SRP values here between zinc and iron, zinc is actually more negative than the iron. And in this case, when those two come together and you add a little zinc to the mix, the iron will become our cathode, and all the bad oxidation stuff will happen over there at the zinc, because it has a more positive, a less positive SRP value. So zinc in this case acts as a sacrificial sort of coating, where all the bad stuff happens to that, keeping your iron sort of intact. You can also do some alloying where you add some other metals to the mix as well, and that can change some of the SRP value of your metal to something more like a noble metal where it's going to be very unreactive. So it can kind of change the SRP value by having a mixture of stuff together, like stainless steel has chromium and nickel sort of added to it. Another way is cathodic protection. So if you could do something like adding magnesium to on a wire to a tank that's buried in ground, like at gas stations and stuff like that, or other places, right? We sometimes bury tanks underneath the ground. Typically the ground is pretty moist, right? Which means there's a lot of water. And that would be bad for a metal that has a value where it's going to be oxidized pretty easily, right? Because then your tank's going to get oxidized, going to pop some holes. You'll be digging up the ground very quickly, right? So you could add something like magnesium to it, where magnesium is a better reducing agent than iron. Reducing agents get what? Reducing agents get oxidized. So if magnesium is a better reducing agent than iron, all the oxidation again is going to occur over here at the magnesium part, leaving your tank hopefully intact and you don't have to dig it up. Again, titanium is used in ship hulls because obviously that's a very salty area that you're on the ocean. Here's a much prettier picture of what I drew there, but you get the idea. Oxidation happening over here away from our tank so we don't have to dig it up every week. Talk.